So what's Hassan suggesting here? So f1 plus f2 plus f3. So we're going to do some scalar multiplication, right? So we're going to try to find a linear combination. So if we want to show that these are independent or not, we can either use Hypatia's suggestion, which is to see if I can easily find a multiple, which it doesn't look like there's an easy multiple that we can choose here. So we got to go the hard way, right? We have to set up a system of equations. So we're going to consider, what is it? Let's just take A times 1, 2, 3 plus B times 3, 5, 7 plus C times 0, 1, 2. And let's set that equal to the 0 vector. And so the idea, if I remember correctly, is that if we could find A, B, and C that were non-zero, then these would be linearly dependent. Okay, so we do suspect that we should be able to find non-zero A, B's, and C's. So let's go ahead and set up a system, and then, yeah, we can maybe just use the determinant, and then we can get this job done. So this would be a system of linear equations that would look like this. So A plus 3b plus 0c, we have 2a plus 5b plus c. And then we have 3a plus 7b plus 2c is equal to 0. So let's consider our coefficient matrix, which is 1, 3, 0, 2, 5, 1, 3, 7, 2. And we could quickly calculate the determinant of this. And so for me, when it's 3 by 3, I usually just add the first two columns instead of doing a cofactor expansion. So I know that I need to do 1 times 5 times 2, and then 3 times 1 times 3, and then 0 times 2 times 7, and then subtraction. So 3 times 2 times 2, that's negative 12, and then 0 times, oops, I missed one. So 1 times 1 times 7, so minus 7, and then minus a 0 times 5 times 3. So in this case, we get 19 minus 19, which is equal to 0. That means that the columns are dependent. The determinant has to be non-zero in order for these columns to be independent and have full rank, if I remember correctly. That's what this particular determinant is saying, right? So the rank of this matrix is less than 3. I might be able to find some leading ones, but I'm not going to be able to get 3 of them, is basically what this is saying. So I know that I can't get rank 3. But but this is a homogeneous system. That's okay. Okay, gotcha. So basically there's 3 possibilities. Either there's a unique solution, or we have no solution, or we have an infinite number of solutions. However, we're working with a homogeneous system. So I know that this case can't happen. I always have at least the trivial solution. So if my determinant was non-zero, that forces me to have a unique solution only, which is the trivial solution. And if the determinant is equal to 0, usually we have 2 possibilities. Either there's no solution, or we could have infinite solutions. But in this case, we're forced to take an infinite solution, which means we should be able to parametrize and find values for A, B, and C that work. So the one that was suggested, which was, 3, -1, and -1, I think, we should be able to multiply that by some scalar, and it should work. Right, so it's not a unique solution, but it is a non-zero solution. Okay, so that's one way to solve that. Now, I think the determinant's probably the easiest way to do it. But let's say my students wanted to see it in a different kind of way. So let's say they set up this matrix, and instead of just looking at the coefficient matrix, they set it up and they make it look like this, right? So this is a an augmented matrix. And we should be able to do row operations on this, and we should be able to also convince ourselves that we get an infinite number of solutions. So we already have a leading one here, which is great. So I'm just going to roll through, just trying to get this in reduced or echelon form, just to see what that would look like. So we could take row 2 minus 2 row 1s, and we could take row 3 minus 3 row 1s. That's going to leave row 1 the same. And that should give us our 2 zeros that we need underneath. So this 5, we would need to subtract 6 from it. This 1, we would subtract 0. This 7, we would subtract 3 row 1s. So 7 minus 9 would be negative 2. 2 minus 0. So we get something that looks like this. Okay, so now I can really easily see that we should get some kind of solution here. So we're going to multiply row 2 by negative 1, and let's take row 3 and let's subtract 2 row 2s. And so we get 1, 3, 0, 0. We get 0, 1, negative 1, and then we'll get a full row of zeros. And then, we could do one last subtraction. I don't think it particularly matters, but the idea here is yes. So we definitely do have a determinant of 0. That makes sense to me. So we could now set up our system, and we could just use back substitution to make this work. So we know that a plus 3b is still equal to 0, and we know that b minus c is also equal to 0. So we're going to set c to be some kind of real number, I guess. It doesn't really matter what c is. But then we can back substitute, and we can find these values for a, b, and c. So if we do set c equal to, if we set c is equal to t, what do we get here? So a plus 3b is 0, right? And then b is equal to t. And so that would mean, I suppose, that a is equal to negative 3t, b is equal to t, and c is also equal to t. So whatever value we choose for c, b has to be the same value, and then a is equal to negative 3 times that first value. So for us, we set t equals to minus 1, and so we got that 3 times the first thing minus 1 times the second thing minus 1 times this thing should be equal to 0, right? So that's what you guys noticed, I believe, right? I forget exactly what these numbers were. So 1, 2, 3. 1, 2, 3, 3, 5, 7, and 0, 1, 2. So this is what somebody noticed. I forget who noticed this right off the bat, but somebody did notice that this should be linearly dependent because we can find some values. Cool. So therefore, linearly dependent.